This is Ms. Phipps. Today we're going to talk about Ohm's law and how it pertains to series circuits. We're going to use Ohm's law to basically work the circuit. Ohm's law states that voltage is equal to the current times the resistance. Okay. Now voltage is this part right here. It's what comes out of the batteries. Remember, voltage is also known as potential difference. It is really more of a change in the potential energy across those points. Current is the charge that moves through the wire. So voltage gives the push. It pushes the charges or the current through the wires, and then the resistors provide resistance. So all those three things together work. Okay. I'm going to make this a little bit smaller so we should have a little bit more room to work with. That's just V equals IR. That is the most common way of writing it. So total voltage can just be added up. So that means our total voltage is going to be equal to 12 volts plus 12 volts. And so our total voltage for this setup is 24 volts. Okay? So there's our voltage, and next thing we're going to do is we're going to find the resistance. In a series circuit, the equivalent resistance, and equivalent resistance is basically, if you take all the resistors, it's the equivalent of one resistor, and in a series circuit, you get to that one resistor by adding up all of the resistance. So it's pretty straightforward. So our total will equal 4 ohms plus 8 ohms, giving us 12 ohms. Now, again, you're always going to start by finding your totals. Okay, and you're going to start with your totals, and then you're going to break it down, and you're going to look at how Ohm's law works over each resistor. So right now we have our total voltage, and we're going to have our total resistance, and we're going to use those to find our total current. Total current, we're going to rearrange that equation just a little bit. Total current becomes current is equal to voltage over resistance. I'm going to take a pause. I'm going to come back up here just in case you don't have it. Let's go ahead and do variables. V, that is volts, and it also has the unit of a volt. I is the variable for current. Its unit is A, which stands for amps, and R is our variable for resistance, and the unit for resistance is the ohm. It's basically the omega symbol, but you say it ohm. Okay, so those are our variables. So our current then is our voltage divided by our resistance, so it's basically just 24 volts divided by 12 ohms. That gives us a grand total of 2 amps. And on a series circuit, you're going to find that the current stays the same. So basically, the path doesn't change, so the amount of charge moving through the path doesn't change. Alright, so it's 2 amps. That's going to be the same everywhere. So that answers the next question. Where in the circuit is the current the greatest? Everywhere. It doesn't change. Alright, so if that's our number 4, now it's asking us a bit more on the relationship issue. If one of the batteries is increased, so with the voltage increase, how is our current? Go back and look at your equation. If you look at your equation, voltage and current are directly related, i.e., if my voltage goes up, so will my current. So that means that it will increase. And the reason why is that it is a direct relationship. Okay. Now, to keep this the same idea, current and resistance. So it says if one of the resistors increases, how's the current going to change? That's going to be decreased. So if resistor increases, current decreases, and that is because it is an inverse relationship. And that is impossible to read. Let's fix that. Okay, so now we have our totals. We have our V total, or R total, and our current. It's not really a total because it doesn't change, it's just the current. Now we're going to use that current and the equation, Ohm's law, to figure out what is the voltage used by each resistor. Because remember, voltage is a potential difference. So as the voltage runs into each resistor, that resistor, the energy is going to be changed. Okay, it's going to be changed from our potential energy, and it's going to be changed into whatever the resistor is going to use. If it's a light, it's going to be turned into light. All right, so basically, the resistors change the energy that's coming through it. So in this case, we have 12 volts coming in. Our resistor is going to change some of those, and then we're going to have some amount of volts coming out. Okay, so how did this work? Let me erase this part again so you can see what I'm talking about. Oh, we'll keep this part. So we got 12 volts coming in, and that means we're going to use V is equal to IR. That means we're going to use 2 times 4, which means our voltage here is 8 volts. Oh, and that was a typo, big typo over here, isn't it? It's not 12 volts, it's a 24 volt. Let's get that cleaned. Okay, 24 volts. So we have 24 volts coming in, and 8 volts are changed by the 4 ohm resistor. So that means we have 16 volts moving on the other side. Now this 16 volts are going to come on down here, and it's going to hit this 8 ohm resistor. So when the 16 volts hits the 8 ohm resistor, it's going to see how much voltage it will use. So it's our current is 2 times our 8, which gives us 16 volts. So we have 16 volts coming in, and now we have 0 volts coming out. And that's exactly what you want to have happen. You want to start with a voltage here, and by the time it comes all the way back around to here, all right, you want 0 volts. All right, that's the way it works. If it doesn't, you're going to end up with a short circuit. Okay, so that's our first one, and then that carries you through the entire thing. We're going to do the second one, and it's going to have a couple of questions interspersed in it.